From the towering peaks of the Himalayas to the vast ice sheets of Antarctica, a dramatic and unsettling transformation is underway. The Earth's majestic rivers of ice are shrinking and accelerating their march to the sea at a pace that is historically unprecedented. This isn't a slow retreat, it's a rapid, violent unraveling of the world's frozen regions. Today, we're diving into the science of applied glaciology, the discipline that measures this alarming speed of change and reveals its profound consequences for us all. The story starts not on the ice, but hundreds of miles above it. The advent of satellites revolutionized glaciology. Before, we could only monitor a handful of accessible glaciers. Now we can track nearly all of the world's 220,000. Satellites like NASA's Landsat have been taking pictures for decades, creating a historical archive. By comparing these images year after year, scientists can create detailed timelines of glacier retreat. For instance, they used this technique to document the 950-meter retreat of the Chota Shigri Glacier in the Indian Himalayas between 1962 and 2008. But we need more than just pictures. To measure volume, we need to know the height of the ice. That's where altimetry comes in. Missions like ESA's CRYOSAT-2 and NASA's ICESAT-2 use radar and lasers to measure the height of the ice surface with incredible precision. By repeatedly scanning the same area, scientists calculate changes in ice volume. It was this data that revealed a shocking truth. Between 2003 and 2019, Greenland lost an average of 200 gigatons of ice per year, while Antarctica lost 118 gigatons. A gigaton is a billion metric tons, the weight of about 10,000 fully loaded aircraft carriers, and these giants are losing hundreds of them every single year. Knowing how much ice is lost is one thing, but how fast is it moving? Satellites can clock the speed of glaciers in two main ways. One is feature tracking, where algorithms follow surface features like crevasses across pairs of images. The other is a mouthful, synthetic aperture radar interferometry, or INSAR. It uses the phase difference between two radar images to detect movement with centimeter-level accuracy. These techniques are how we discovered that Greenland's Jakobshavn Glacier was clocked moving at 150 feet per day in 2012, nearly 3 times its speed in the 1990s. Some radar frequencies can even penetrate deep into the ice, reflecting off the bedrock below, allowing scientists to create detailed maps of the subglacial world, which is critical for understanding why glaciers flow the way they do. Despite the power of satellites, there is no substitute for getting your boots on the ice. Fieldwork provides the ground truth that calibrates and validates all that satellite data. The classic way to measure a glacier's health, or its mass balance, is to install a network of ablation stakes. These are long poles drilled deep into the ice. By measuring how much of the stake is exposed at the end of the melt season, scientists get a precise measurement of ice loss. In the higher altitude accumulation zones, they dig snow pits to measure how much new snow has fallen. For a glacier to be stable, accumulation must equal ablation. But for 37 consecutive years, the world's reference glaciers have lost more ice than they have gained. The system is profoundly out of balance. To track movement on the ground, glaciologists use high-precision GPS units. By leaving a receiver on a glacier, they can measure its velocity and how it changes, sometimes even observing daily cycles in its flow. And to see what's inside and underneath, they use geophysics. They drag ground-penetrating radar systems across the surface on sleds to create detailed cross-sections of internal layers. Or they use seismic surveying, sometimes with just a sledgehammer blow on a metal plate, to record sound waves that bounce back from the bed of the glacier. This reveals not just ice thickness, but whether the glacier is sliding on hard rock or soft water-saturated sediment, a key factor controlling its speed. A new field, passive glacial seismology, even uses sensitive instruments to listen to the creaks, groans, and water flow within the ice, giving insights into processes like iceberg calving. To truly understand the speed of today's change, we must look to the past. And for that, we turn to ice cores. Glaciers are unparalleled archives of Earth's climate history. Using specialized drills, scientists extract cylinders of ice, sometimes miles long, that contain a layered record of millennia. Each layer is a year's snowfall, and its chemistry reveals past temperatures. But the real treasure is trapped inside, tiny bubbles of ancient atmosphere. By analyzing these bubbles, scientists can directly measure past concentrations of greenhouse gases like carbon dioxide. It's from ice cores that we know today's CO2 levels are higher than at any point in at least 800,000 years. This is the irrefutable context that proves today's warming and glacial melt are a stark anomaly. So what is the final verdict? The collective evidence paints a globally coherent picture. The world's ice is vanishing at a speed that is accelerating decade by decade. Let's start with the giants, Greenland and Antarctica. Together, they hold enough ice to raise global sea levels by over 200 feet. A landmark project called the Ice Sheet Mass Balance Intercomparison Exercise, or IMBIE, combined data from multiple satellites to get the most complete picture of their loss. The results are staggering. Between 1992 and 2017, Greenland and Antarctica shed a combined 6.4 trillion tons of ice, raising global sea levels by 17.8 millimeters. But the most alarming finding is the acceleration. The combined rate of ice loss increased six-fold, from 81 billion tons per year in the 1990s to a staggering 475 billion tons per year in the 2010s. The polar ice sheets alone are now responsible for a third of all sea level rise. In Greenland, warmer air melts the surface, creating rivers of meltwater that pour into the ocean. At the same time, warmer ocean water attacks the edges of glaciers, causing them to speed up and calve more icebergs. In Antarctica, the main culprit is this warm ocean water getting underneath the floating ice shelves. These shelves act like a cork in a bottle, holding back the glaciers on land. As they thin and weaken from below, the cork is removed, and the glaciers accelerate into the sea. Beyond the poles, the world's 220,000 mountain glaciers are also in rapid retreat. A 2021 study in the journal Nature found that between 2000 and 2019, they lost an average of 267 gigatons of ice each year, accounting for another 21% of observed sea level rise. And here too, the speed of loss has doubled in just 20 years. In the Himalayas, recent ice loss is at least 10 times faster than the average rate over preceding centuries. In the European Alps, some projections suggest 80 to 90% of glacier ice could be gone by 2050. In the tropical Andes, glaciers have shrunk by 30 to 50% in just 30 years. And Alaskan glaciers are losing mass faster than almost anywhere else, with the retreat rate of some quadrupling. This isn't an abstract problem. The consequences are immediate and dangerous. As glaciers retreat, they leave behind depressions that fill with meltwater, forming unstable glacial lakes, often dammed by nothing more than loose rock and debris. When these dams fail, they unleash a catastrophic event called a glacial lake outburst flood, or GLOF. The Himalayas are a global hotspot. In June 2013, a GLOF in Uttarakhand, India, contributed to devastating floods that killed over 6,000 people. In February 2021, another event in the same region killed over 200 and destroyed 2 hydropower plants. And in October 2023, a lake burst its banks in Sikkim, causing a major dam to collapse and killing over 100 people. Scientists warn that as the number and size of these lakes grow, the risk is accelerating. Another consequence is water scarcity. For hundreds of millions of people, glaciers are frozen water towers, storing water in the wet season and releasing it in the dry. As they shrink, this system is breaking down. Initially, increased melting can boost river flows, a phenomenon called peak water. But once a glacier shrinks past a certain point, runoff begins a terminal decline. Cities in the Andes are already feeling this. La Paz, Bolivia, relies on glaciers for up to 85% of its water in the driest months. It has already faced severe water rationing. In Central Asia, meltwater supplies around 80% of the river runoff for major arteries like the Amu Darya and Sir Darya, which support agriculture for millions. By 2050, the flow of these rivers could be significantly reduced. Of course, the most far-reaching consequence is global sea level rise. All this melting ice has to go somewhere. The IMBIE team found that the rate of ice loss from the ice sheets is tracking the IPCC's worst-case warming scenario. If this trend continues, the ice sheets alone could contribute an additional 17 centimeters to sea level rise by 2100, putting 400 million people at risk of annual coastal flooding. As the crisis accelerates, so does the pace of innovation in glaciology. Scientists are using artificial intelligence and deep learning to speed up complex glacier models by a factor of 1,000. This allows for better and faster predictions of future sea level rise. A new generation of satellites, like the recently launched SWAT mission and the upcoming NASA Indian NISAR mission, will provide an even clearer view of the cryosphere. And to overcome the dangers of fieldwork, scientists are turning to robotics. Autonomous boats and remotely operated vehicles can get close to calving glaciers, while researchers are developing cryobots, probes designed to melt their way through miles of ice to explore hidden subglacial lakes. Applied glaciology is a science in a race against time. The data its practitioners collect is not academic. It informs global climate policy, coastal defense engineering, and water management strategies that affect billions. The message from the world's ice is unequivocal and delivered with stunning clarity. The alarming speed of modern glacial change is a direct consequence of a warming planet. The challenge now lies not in understanding the problem, but in our collective will to act on the urgent warning our melting glaciers have delivered.